Welcome everyone. My name is Simon Dora. I'm from the Johannes Kepler University and I'm working towards my PhD at the Institute for Integrated Circuits and Quantum Computing. And today I want to give you a short introduction to open source tools in chip design. So what are free and open source software or FOSS and what tools are available? So, for example, in this next slides, we will focus on the digital flow only. So I will point out the most important digital flow open source tools. In this case, Verilator, this is a Verilog code linter, Icarus Verilog, which is a Verilog compiler and simulator. Then we have waveform viewers, in particular GTK Wave and Surfer. Then we have also for VHDL, we have an analyzer and compiler, a simulator and a synthesizer, and this is called GHDL. Then with IIC and ABC, we have a Verilog synthesis tool. More particular with IIC's Slang, we also have a system Verilog synthesis tool. Then we have Magic and KLayout, which are layout editors with design rule checks and parasitic extractions, where we can look so not only editors, but also viewers, of course. So we also can check our final layout in the end. Then if we don't want to make a chip, but for example, flash an FPGA, we can use NextBNR, which is a place and route tool for FPGAs, in particular for lattice FPGAs. And then we have LibreLane, which is a complete digital RTL to GDS flow. And all these tools are integrated into this IIC-OSIC-TOOLS Docker container. And this is an all-in-one Docker container for free and open source software-based IC designs, but not only for digital, but also for analog circuits and of course analog mixed signal designs. But as I said before, in this tutorial, we will focus on the digital design flow. So here we have an overview. We have the custom design flow and the semi-custom design flow. And we have in total 3 PDKs, which I will go into detail afterwards. The custom design flow is more for the analog part. So here we also have schematic entry with Xscheme or QS, and we have analog simulation with ngSpice, XICE, or Case, and more recently also Wackask. And then of course we again have layout editors like Magic, KLayout, and GDS Factory. And then we also have our tools for design rule checks, layout versus schematic, and parasitic extraction. But in this tutorial, we focus on the semi-custom flow because this is the digital design flow. And as pointed out before, for the digital simulation, we have eVerilog, Verilator, GTK Wave, Surfer. And for synthesis, we have IIC or IIC Slang, GHDL, and ABC. And there are certain RTL to GDS flows, for example, OpenRoad, OpenRow scripts, QFlow, Silicon Compiler, OpenLane 2, and the wrapper for OpenLane 2, and with some more advanced stuff is LibreLane. To understand the open source tools more in depth, I want to have a rough overview on the Y chart. Here we can see that there are different levels of complexity. So in the end, we want to have a transistor layout, of course. So we are at the lowest level. But we are starting at the register transfer level with our HDL code. For example, in Verilog or VHDL or whatever other HDL language are out there. And then we go to the gate level where we have the logic, and then we have the transistor level. where we have the transistors, of course, parasitic extraction and stuff like that. And for example, IIC-OSIC is doing the behavioral synthesis, the RTL synthesis, and the logic synthesis. And the GitHub repo and the documentations are linked here also. I just wanted to point out what we actually do here in the background. So in the end, you will see we just run a command, and there is a Verilog code, and drops out or pops out a layout with on transistor level. But it is, I think, a good idea to also understand what in the background is also what the background is doing or what is happening under the hood. As I said, we also have next PNR in the Docker container. So we, for example, can flash an lattice FPGA. And this is also quite interesting because, I mean, you can simulate your Verilog design, of course, with ATK for Surfer. And you also can double check your hardware stats with IICs after synthesis. But before really making a layout and taping it, it is a good idea to, for example, flash it on an FPGA and test it there. And when the FPGA design also works, then we can say with a high percentage that we will have a functioning digital layout in the end. How does the RTL to GDS flow look? So as I said before, we have an hardware description language in whatever language we want to have this. And then a logic synthesis has to be performed. Then the floor planning, placement of the components, the clock desynthesis, and routing. So these are the overview steps RTL to GDS flow uses. I will show you later that there are a lot of different steps and different software tools or open source tools involved along the way. After routing, we do a parasitic extraction and we make a static timing analysis and a post-layout simulation. And if, for example, the timing requirements or area requirements are met, then we are finished. Otherwise, we make another design iteration, change the config settings and do this synthesis procedure again. In the end, we make a physical verification and then we are ready to tape out our digital design. And this flow is done by LibreLane. We have also a GitHub repo for that and the documentation, of course. And here, LibreLane, the main idea for LibreLane is that you have an idea, you write your HDL design, and in the end, you have a tape out which you can manufacture. And of course, you can use LibreLane with many advanced options, but the simplest way should be to execute one command, enter your Verilog code, and insert your Verilog design, and the layout drops out in the end. And this is what LibreLane actually can do. So this is the flow diagram. We input our Verilog design, for example, and a config JSON file. So in this JSON file, we have the die area, we have the area utilization, we have the clock timings and stuff like that in there. So, for example, what is my clock port, what is my clock period, and stuff like that. Then we do a linting of this Verilog code with IICs and Verilator. And then we basically use OpenRoad. So you see, LibreLane is a nice wrapper over a lot of different open source tools. And this also demonstrates the cool and versatile characteristic of open source IC design or in general open source software. You take the software that's available and build some really nice flows around it. And in this case, LibreLane. So We use OpenRoad, which is basically the flow I showed you before with floor planning, placement, clock tree synthesis, routing, ASCII extraction, and static timing analysis. And then we additionally have a physical sign-off. So we have a layout as a schematic and a design rule check with Magic, CarLayout, and NetGen. And in former days, LibreLane was actually called OpenLane, or OpenLane 2 is then the advanced version of OpenLane. But in the beginning of the year, eFabless was shut down, and due to naming, copyright things, um, OpenLane was renamed to LibreLane. Just in case you are wondering why there are so many different lanes, this is just what happened. Yes. And here we see what how many different tools are used under the hood. And these are probably not all. This is just also a small list. So you can see for static timing analysis, we have OpenSTA. For clock tree synthesis, we have Triton CTS. For parasitic extraction or stuff like that, we have OpenRCX. For LFS check, we have NetGen. So we have a lot of open source tools laying around and are used within these flows. And this is what's happening under the hood. So don't underestimate open source tools. A lot of effort goes in here, and some tools are uh, really nice designed, and also in terms of complexity and stuff and speed. And some of these open source tools are, I don't want to say better, maybe some of them actually are, but they are nearly as good as commercial tools. Um, yes. So in the future, I think we will see a lot of nice and huge chip designs only done in open with open source tools. And I think if you look at the ETH Zurich with the Pulp platform, you see already huge CPUs and digital designs done with only open source software. And of course, when we want to use all these open source tools practically, we need a process design kit. Without a process design kit, we cannot tape anything. And this is also the reason why it took that long that open source has been established in chip design. I mean, a lot of these tools I yeah, listed before are here since many years. Actually, Magic, I think, was the development of Magic, I think, was started in the 80s or 90s. So the software was around quite some years now. But the main bottleneck was the process design kit. And I think in the year 2020, Skywater released the first open source PDK, which was an 130 nanometer CMOS process. And I think 1 year later, Global Foundries published their 180 nanometer CMOS technology. And I think in 2023, IHP, a German company, published their BiCMOS technology, which is 130 nanometers. And with these PDKs, it is now possible to tape out the digital designs, but not only digital, also analog or analog mixed signal. So now we really can use our designs practically and not only theoretically. And this makes teaching or this makes chip design for teaching and hobbyists really interesting now, because you basically can design any chip at home in your garage or whatever. And for teaching, this is also quite nice because now the students can work everywhere and whenever they want. Before that, we had specific computer labs where the students can work on Cadence, for example, but only, yeah, they have to come to the university or the campus when they want to design their chip. And now this is really flexible. Furthermore, we don't need to sign any NDAs. No non-disclosure agreements are needed anymore, um, meaning that um, bachelor thesis or master thesis can now also be published openly. And this is quite nice because many students are really motivated and making really nice designs or IP blocks. And when they are under an NDA, they are sometimes thrown in the drawer and never get out then. And they're just not public. And now every other student on the world or designers or hobbyists can use this thesis or this resulting IP block from the thesis to use it in their own designs. So this was the main bottleneck, and now we finally have process design kits. What are these kits? So in these kits we have device parameters and simulation models for components, for example, PSIM or PSP. For example, PSP is used in the IHP technology. And not only simulation data is in there, but of course also layout data. So we have design rule check, for example, minimum track width, minimum distance, minimum contact area, whatever, minimum antenna regulations and stuff like that. We also have layout versus schematic rules, and also the electrical rule check is defined in the process design kit. And now the question is, when we have a design, where to tape out. So we can, for example, tape out a tiny tape out. This is increasingly popular and is maintained by Matt Twain. We have the opportunities for the Sky 130 and for the IHP 130 BDKs here. And Tiny Tapeout is a multi-project chip. So you have one die with a lot of different projects on there, and they can all be selected individually with a max. So all designs are open, available on GitHub, and everyone who buys a chip and evaluation board can in the end test other designs, which makes it also really nice for teaching or for the academic way. So for example, you design an ADC and someone designs an DSC, you make an ADC DSC system along the way when you have two different PCBs, for example. And you can really learn a lot from this. And the costs are also quite cheap or quite low because many projects are on one die, so you basically share the costs for the die. And then there's also Chip Foundry, which uses the same principle, and I think it supports the Sky 130 and the Global Foundries 180 PDKs, and is also for multi-project chip. And then we have Europractice, and I think Europractice is doing the multi-project wafer approach. And you also can tape out commercial PDKs there. For example, TSMC with really flagship PDKs down to several nanometers. But of course, these tape outs are then quite expensive. To show some examples, we have at university, at our institute, there was this popular SAR ADC developed 2 years ago, I think, by Manuel Moser. And we also have this synthesizable digital temperature sensor. And the SAR RDC is an analog mixed signal design. And this design really shows what open source tools are already capable of. And this looks already quite impressive. Then, of course, we have Tiny Tapeout. We have here the die for the Tiny Tapeout 3 project. And here we can see we have many different projects. Some have more hardware in it, some have less hardware in it. And if you buy one tile or one PCB with a tile on it, you can test all designs with the max, which can be seen on the left bottom corner. And now the tutorial part starts. So how can you design a digital chip and tape it out afterwards? So I would recommend if you, I mean, this is for Windows 11 because I'm a Windows user. But of course, within the container, you then have to use Linux. So if you're a Windows user, then I would recommend to install the Docker with the provided link, download the IIC-OSIC-TOOLS GitHub repo, start the Docker container, navigate to the IIC-OSIC-TOOLS and open the command line, enter this /start_x.bat, and then the recent image of our IIC-OSIC-TOOLS container is installed. And depending on which of the three BDKs you want to use, please also set up the design init file within your designs folder. I will show you afterwards on a real on a live demonstration. In case you never have used Linux somewhere, then here is a Linux cheat sheet with some useful commands here. I mean, I think you should get along pretty well with the container and this list. If you need some more advanced commands, please check out the Geeks for Geeks link down below. And this is now the recommended workflow for a digital design. And I provided a GitHub repository here because this is also with some files and some scripts. So the process is getting more convenient, easier, and faster. And the reason for this video actually is also that we are currently teaching this in a university course, which is called Integrated Circuit Design. And feel free to check out this GitHub repo, download these files, and then you can design your chips also locally. So the first step is, of course, write your Verilog design and simultaneously always simulate this design in GTK Wave or Surfer. Then afterwards, synthesize the design with IOSIS and check out the hardware statistics. If these, for example, AND gates and registers are roughly the number you have imagined for your design, then we can say, okay, the design is good and there is nothing unexpected. This is especially interesting for beginners because there might be the thing that some beginners have a software programmatic background and then they want to divide, for example, something. And as you probably know, in digital design, a division is really complex. So normally you use shift operators or a codic IP. But of course you can use a division symbol and then the synthesis tool is doing something with it. And for example, building a huge divider with a lot of logic, and then you will see in the IOSIS hardware statistic that there might be something odd here. Then optionally, you should test your Verilog design on a Lattice FPGA board with NextBNR. And when these steps are verified and everything is still working, then you can generate your GDS with LibreLane. Or what is also quite nice, there are templates for Tiny Tapeout in GitHub for IHB and Sky and for Verilog. So you can upload your Verilog code to these GitHub repos and then run your GitHub actions. And then also the GDS is generated with LibreLane in the background, and you will also have a nice 3D viewer or 2.5D viewer, where you can verify and check out your layout. And finally, you also can do, because after the LibreLane flow, there is a final Verilog netlist with the which is also used for L4S, layout versus schematic. And this netlist in the end contains, for example, additional registers or buffers, for example, if they are needed for for the clock tree synthesis or for the clock tree itself. Then you in the end can also simulate this Verilog netlist again with GTKW for Surfer, for example, and check out if still everything works. If your Verilog entity or module or architecture is finished, it should be compiled and checked for syntax errors, and not only for errors but also for warnings. In chip design, this is crucial. I mean, I sometimes ignore warnings. I think everyone has done this once in his lifetime, to ignore a warning, but you you still can ignore the warning, but you have to understand it. This is the difference here. So read through the warning. If you understand the warning and you see, okay, this warning doesn't really matter for me, then you can ignore it. Or set a flag in the linter's shell that this warning can be ignored. Then you manually, more or less, allow this warning, deactivate it. Then every time a new warning pops up, you see it. So try that the output after the linting is always clear. And of course, we have to simulate the architecture. So when there are no syntax errors and warnings, we can simulate this with an additional Verilog test bench. And normally you would have to enter the following commands. So we use Icarus Verilog, and then in the Verilog counter test bench we dumped the .vcd file, and we can then open this in GTKWave or in Surfer. And I mean, the linting alone can be done with the IIC for lint shell. And if you want to simulate, there is also in the simulate I provided a shell. Also in the GitHub repo, this is all available in there. And in this simulate shell, you also have a linting at the beginning. And if you load the VCD file with GTKWave, then you can save it with Control S or reload another VCD file with Control O. And alternatively, if you want to use Surfer, just enter Surfer in the command line and then manually load, for example, the .vcd file. And the simulate shell looks like this. So just the codes I have presented before, or the commands I presented before, is now more or less generic with an input name. And if you execute this, you have a linting, you have a simulation, and you immediately open GTKWave. And GTKWave, for example, looks like this. So you can display your constants, parameters, and your signals, for example, clock, reset, and in this case, a 3-bit counter value at the output, because this is a generic counter we have provided in this tutorial. And of course, if this is more convenient for you, you can use Surfer. Surfer was developed recently and has a more modern or fresher looking GUI. So if you're more into Surfer, then of course you also can use Surfer for digital design simulation. So we can now show hardware statistics or stats with IICs. This is also pretty straightforward. You navigate to your folder where your Verilog counter module is located. Then you enter IOSIS, you enter read Verilog, and then your module of the Verilog code. Then you make a process with proc, and then you print the statistics with stat. And then the statistics are printed for your Verilog design, and this then should be reviewed carefully and validated, or if this is okay with your design, and if this is okay what you would have been expected from your Verilog module. And since this is quite cumbersome with 4 different commands, I also provided a shell script here. So just enter uses underscore stats.shell and then counter, for example, in this case. And this now reads the Verilog file, processes it, optimizes it, flattens it, and also makes a pass to a tech map. And then we can again print the statistics. And here we now have the component count from the tech map, which is more precise with only process and stats on the real solution in the end. And in this case, there is printed the hardware for an 8-bit counter, and we see the 8-bit registers in there with some additional logic, and of course some wires to interconnect everything. And you see here that we have some dollar signs and then and, max, not, or, and stuff like that. But then there's also SDFF. And if you are not familiar with these abbreviations, then you can have a look at the IOSIS manual, which is also included in the GitHub repo or can be found in the internet and Google. Because this IOSIS manual describes all these abbreviations. For example, DFF is a D-type flip-flop, but ADFF is a D-type flip-flop with asynchronous reset, and the other one has a synchronous reset. This is just a small list here I provided, but in the manual, as I said, there is a comprehensive one. So if you don't understand the output in the statistics, then check out the manual. And then we come to LibreLane. As I said, in the config JSON, you, for example, set the clock period, the clock board, the die area, or the target density. And then with a simple command, so you navigate in the LibreLane folder with this config JSON. And of course, in the config JSON, you also set the destination of your Verilog file. And then with LibreLane -- manual pdk config.json, you run the flow. And then the result are some folder structures I'll show you afterwards. And depending on your design, after minutes or hours, the design should be created, and it can be viewed in 2D with Magic or Car Layout, or in 3D with GDS 3D, or as I said before, with tiny tapered GitHub actions. And these GitHub actions work quite nice. And if you are interested in Magic, or if you use Magic as an layout viewer, then you also can check out the Magic cheat sheet for the commands and how to handle this tool. And I also provided a shell script for which is called run_LibreLane. I mean, executing LibreLane is only one command. This is already quite simple. But if you now want to change between BDKs, then you can also do that with our IIC-OSIC-TOOLS specific scripts. For example, this SAC BDK script, and then you can enter, or you can switch to a Sky 130 BDK, because at startup, by default, currently the IHB BDK is loaded. And if you don't, as I said before, if you don't use the design init file, you at least can do this here to switch to the Sky 130 BDK. And by executing this shell, you switch to the new BD to the Sky130 BDK and you run the LibreLane flow. And then the output is a folder structure like this. So you in the LibreLane folder where the config.json is located, there is a runs folder created, and in this runs folder, all the different runs are saved. And if we take one, we have a lot for every flow cycle. I think there are 78 now. A new output folder is added for every step in the way or on the way. But we are interested for the final output. And in this final folder, we, for example, have a GDS. We have for Magic, we have the Magic GDS, SDC, SDF. We have a spice file. We have a lot of nice stuff in here which we can use for um, further processing. For example, if we want to use this digital core for an analog mixed signal simulation and stuff like that. And if we, for example, go to the Mac folder and execute magic counter.mac, we, for example, get the layout for 8-bit counter. And in this case, the layout is 160 times 100. This is set with the die area flag in the config.json because one dial for tiny tapered is 160 times 100 micrometers wide and long. And again, for a nice 3D view, use the GDS view of the tiny tapered GitHub actions. I mean, you also can use GDS 3D, as I said before, but I don't know why sometimes I get a lot of segmentation faults here, and this sometimes gets really annoying. And since these GitHub actions work quite well, I'm using this more often now. Thank you very much for your attention on this presentation, and now a live demonstration on the tutorial will follow. So in this step, we are now installing the Docker desktop for Windows and also the IIC-OSIC-TOOLS container. So first, go to the Docker online page and download the exe here. And in the meantime, you can also go to the GitHub IIC-OSIC-TOOLS page and download the zip file. Then you can go to the downloads folder, and here you can unzip the IIC-OSIC-TOOLS, and then you can install the Docker on your PC. So I will do this now live, but I will cut it in the video afterwards so that it's not that long in the end. So when this installation is finished, we can close this window and we can open the desktop app. So this is for the opening process, yes. And then you, for example, can sign in. I will do this right now. Go to the desktop Docker. And so now I've signed in with my Gmail account. And I mean, I think you can sign in, but you don't have to. Then we can close this. So now the Docker is setting up everything in the background. And while this is happening, I will show you the start_x.bat file. In this folder, we can now open a terminal. And here we now can enter this following command. And now it says, okay, it does not exist, and every file is now downloaded and installed. In the meantime, I show you the Docker desktop app. When everything is installed here, we will see an image here, and here we see then a container, which then can be run, and within this container, we can then use all the open source tools that are available for the IIC-OSIC tools. And as I have you shown before, there are quite a lot. So these are the installed tools, and the list is pretty long. And if you're not using Windows, but for example, some other system, then you have a quite comprehensive README where you can check out how to install everything. And if you want to switch between PDKs, here is the code for that. Or you just go into the GitHub repo I have shown you before. And in here you also have the design init file with all the code you need. And as I said, by default, the IHB BDK is loaded by the Docker container. And at the startup, the design init is loaded. And here now it is switched to the Sky BDK. If you want to have the IHB BDK, just use this code here. And if we have installed, so if this is finished and we have an image and a container here, then there will be a designs folder created under users, EDA and designs. And if you install the Docker the first time, then this folder will be empty. And here, for example, we have now the folder from the GitHub repo and the design init file. Just to understand where you're working now. And within here, you have your, for example, Verilog folder with the source folder of the counter and the test bench of the counter, both in Verilog. Here you have the simulate shell, and in the source folder, you have the uses stats shell. And then, of course, we have LibreLane here with the run LibreLane shell, and the config JSON is also in here. So yeah, here you can enter the design name and where it is located, die area, the place density, log period, log port name, and stuff like that. And this is more or less the config JSON file from the tiny tapeout GitHub repository template. And now I'm waiting until everything has been downloaded, and then we'll show you how to execute the scripts. And then we are basically finished with the counter tutorial, and then you can swap out the Verilog code and enter or insert your own Verilog design. So when everything is downloaded, this should look like this in the Windows shell or in the Windows command line, and we can close this, and automatically the Docker container terminal opened. And now let's have a quick look in here. So now we have the image, which has been created 3 days ago. So this is the September update. And then we have our container in here. And if we close this, then we every time can start our container here. So now the IIC-OSIC-TOOLS container is installed. You only have to start the Docker software, so desktop software, and press the play button, and you're good to go. And now we are in our FOSS designs folder I have shown you before. If we enter ls, we see all the folders in here. And we now want to go to, of course, our GitHub repository. And now I want to show you first how to simulate the Verilog design. So we go into Verilog and test bench. And when we open this here, we see the test bench and also the simulate shell. And since this shell script is provided, we just execute it with an additional parameter of the name of the Verilog module, in this case counter. And then we see that it has been linted. And then the steps I have shown you before in the presentation are executed. And now we have the GTK wave viewer opened here with our counter test bench. And here we have the parameter. So we have simulated a 3-bit counter with the clock signal, a reset, and the output signal. And we, for example, can multiply it or copy it or duplicate it. And for example, can also set it to decimal. We can insert, for example, a command like signals, and then we can shift it up here. And for example, another one for, I don't know, constants. And you can then save this with Control S. And in this case, this is the counter GTK wave I have saved before. And if you now want to reload a GTK wave file, you can press Control O and use this. And this is added on top of the already loaded signals. So when we delete all again, we can again press Control O, get the GTK wave in here, and then the signals are loaded. And then, as I said, we also can open Surfer, press this open file icon here, and then we go to the test bench folder and click on the .vcd file. And here we also have, for example, now the bit width, the clock, the reset, and the output value. And we, for example, can scroll with Control and the mouse wheel. So this is also a really nice looking view. And of course, you also can color the signals if you want. You also can insert a divider with, for example, signals, and enter this here. So this is also possible like in GTK wave. So this is up to you what you want to use more. This is their own preference, I guess, if you want to use GTK wave or Surfer. Now the simulation of the Verilog module worked, and maybe just take a short look into the Verilog code itself. So this is a simple generic counter, so we can set the bit width here. If there's no bit was specified. By default, it's an 8-bit counter. And the test bench is also quite simple. We set our signals here. So first we reset the counter, and down here we deassert the reset after 50 nanoseconds. This has also been shown in the simulation before. And here we set the bit width to 3 bits, as also shown in the simulation before. And now we want to see the stats of our Verilog 8-bit counter. That's why we navigate to our source folder now, and we execute our shell file for the stats. And this is also done quite simple like this. And here we see that our 8-bit counter, as expected, has 8 registers and some additional logic. So this is now also verified. Now we want to do a layout here. So we go to our LibreLane folder. Go one back. And here now we have our config.json. And when we now enter the LibreLand flow with -- manual BDK config.json, this should already work because we have the Sky BDK loaded in the design init file. If there is no design init file and now the IHB BDK is loaded, we can execute again the provided shell script. In this case, just run underscore librelane dot shell. And now we see the different stages. We have 78 stages from synthesization to floor planning, place and route, log tree synthesis, and whatnot else. And to skip this, in the meantime, I'll show you an existing folder. So as I said, we have for nearly every 78 steps, we have a subfolder where you can see netlists, or for example, here we open the user synthesis folder. And in every folder, we have a log file, of course, and then the files contained for this cycle. And in the final folder, we, for example, have a GDS file, or if we want to open it with magic, we have the magic file. And yeah, much more. We have a spice file if we want to include it into another analog mixed signal simulation and stuff like that. And we, for example, can do this now. And we can open the GDS file with magic, for example. So we say, okay, I want to go in the runs folder. And I also want to open the final folder. And I want to go to the magic folder, and now we can open this with magic counter.mag. Exactly like this. With F we can zoom in here and we can disable, for example, subcells, and then we have our layout here. So these are some standard cells, and also down here, and also with the labels. And then of course we have some power and ground traces also here. Exactly. So now every script I have provided has been executed successfully. We have run Rebelane and our magic layout. We can now have a look here. Yes, so Also the new liberal inflow ran through, antenna is passed, LVS is passed, and the design rule check is passed. I mean, we have some warnings here, and this is now again the place or the time where you should review and validate these warnings precisely. But other than that, I think everything is working. And if you have some questions, please feel free to comment down below. And we will try to help as fast as possible. Otherwise, happy designing and see you soon. Bye.